So, Jai Hind everyone. Myself Ritesh Sharma. I am from Ajay Kumar Engineering College, Ghaziabad. So, today I am here to discuss a important topic on resonance. So, the resonance in the AC circuits. This is our topic. The resonance in the AC circuits. Okay. So, this is the one of the important topic of the unit number second unit, that is called the AC circuits. So, let us start with the resonance in the AC circuits. So, in the resonance, we have seen that two types of basic resonance that we have already observed. First is called the series resonance, and the other is the parallel resonance. Okay. So, series resonance means when the circuits, when the RLC are in the circuit in the series, and then the series resonance occurs, and when this inductance, the reactive elements like inductance and capacitance are in parallel, the parallel resonance occurs. So, let us discuss the series resonance and the parallel resonance. So, in the resonance, if we talk about, that is the resonance in the AC circuits containing the reactive element L and C, that is said to be a resonance when the circuit power factor is unity. So, whenever the resonance occurs in a circuits, AC circuits, the voltage and the currents are in the same phase, and the voltage and the current are in the same phase. That means the angle between the two is almost zero. Then the power factor, which is called the cosine of the angle between the two, is equal to unity. That is called the power factor is unity. So, as I just told you that the phase angle is zero or the power factor is unity. That is called the circuit is electrical resonance. Now, if this condition exists in the series circuit, it is called the series resonance. You can see that when this condition exists in the series circuit, it is called the series resonance. On the other hand, if this condition exists in the parallel AC circuit, it is called parallel AC resonance. Okay, so that means the series resonance and the parallel resonance are depending upon how the circuit occurs, whether it is series circuit or parallel circuit. And the frequency at which the resonance occurs is called the resonance frequency. Whenever the resonance occurs at a particular frequency, we call it as a resonance frequency. Okay. So, let us discuss the series resonance and the parallel resonance. So, first we discuss the series resonance. In the series resonance, in the circuit, you can see that we have the three component, the resistance, inductance and capacitance. These three elements are in series. So, the current flowing in the circuit is the same. The voltage across the resistance is VR, the voltage across the inductance is VL, and the voltage across the capacitance is VC. So, you can easily calculate the, first of all, you can calculate the impedance, that is the input impedance we call, is equal to the resistance plus inductance and its the resistance plus inductive reactance and capacitive reactance, that is R plus XL plus XC, GXC. So, you can find this is the impedance of the circuit R plus this is the R is the real part, and this omega L minus omega C is the reactive part or the imaginary part. So, at resonance, as we know that at resonance, the net reactance becomes zero. That means this part will become zero. When this part, because whenever the resonance occurs, the voltage and current are the same phase. That means the total impedance will be equal to the resistance, that is R. It means that this imaginary part will be equal to zero. When we equate it to zero, that is at this resonance frequency, when we equate with this, it will comes out that the omega R, which is called the angular frequency or the angular resonance frequency, will be equal to 1 upon under root LC in radian per second. And if we want to calculate in the hertz, that is frequency, it is 1 upon 2 pi, because omega is equal to 2 pi f. So, from here the f will be equal to your omega upon 2 pi. And this, as I told you, that the unit of this omega r is in radian per second, and if we talk about frequency f, that is in hertz respectively. So this is a simple circuit as far as and how we can calculate the resonant frequency of the series RLC circuit. Let us go further. Now, if we talk about some key features of the series resonance, if we talk about the series resonance, some of the features like XL is equal to XC. We have seen that in our previous slide. We have found that the omega L is equal to 1 upon omega C. That is, XL is equal to XC. So omega L is equal to 1 upon omega C. It means that when the two reactances are equal, then when at resonance, these two reactants must be same. Then we can find the resonance frequency, which is equal to 1 upon 2 by under root LC. Of course, in hertz it is. Then at this particular resonance occurs, the impedance is minimum. We can see that the impedance, which is ZR, R is that is impedance at resonance, which is minimum and is equal to R. Why? Because XL is already equal to XC. So in the previous slide, when this is equal to this, the Z must be equal to R, which is minimum. And when the impedance is minimum, the current, the circuit current will be maximum, will be equal to V by ZR. So this is the maximum condition. So hence at resonance, in series resonance, the current is maximum. And when the current is maximum, of course, the power dissipated in the circuit is also maximum. Of course, the power factor is unities because the angle is 0 degree. And the power factor is cos of phi, that is cos 0 is unity. So that means the circuit is purely resistive. As we have seen that the circuit is purely resistive. Another point is that since in the series resonance, the current flowing in the circuit is very large, the voltage drop across L and C is also, when the current is increases, the voltage drop in the inductance and capacitance is also very large. But they are in opposite directions. Okay, if we draw the phasor, this voltage VL and VC will be equal but in opposite direction, and but this amount is very, very large. Okay, and this amount is also much greater than that of the applied voltage. So however, the voltage drop across IL and C combination as a whole will be 0 because this drop equal in magnitude but 180 out of phase, as I just told you that. So this voltage drop, the important part is that this voltage drop across inductance and capacitance is very, very high than the value of called input voltage or supplied voltage. So these are the some key features of the series resonance. Now let us discuss about the some characteristics in the series resonance. In series resonance, we know that suppose that if we are drawing the some characteristic like reactances and frequency, how this, since the voltage is constant in a resonance, what happens, this if we draw the characteristics of this some reactance is called XL, which is equal to omega L. Suppose if we want to draw the characteristic of XL with omega L, since the value of L is constant, but this XL you can say is proportional to the frequency. What is omega? Omega is a frequency. Okay, it means that when we draw the variation, when we vary the frequency, we can plot this XL, and we found that it is linear. Since XL is proportional to F, it is linear. So linear means it will follow this curve. This is for XL, you can see in the picture. Another point is that if we talk about the XC, XC is inversely proportional to frequency because it is 1 upon omega C. So 1 upon omega C is, in fact, XC is inversely proportional to the frequency. It means that it is some called rectangular hyperbola, and we know that the XC is always negative. We always take XC is equal to minus of J XC, or reactance is minus of this. So we always take that in the fourth quadrant. XC is like that This is our Xc, how it is. So this is our frequency. At this particular frequency, our XL is equal to X, this frequency. This both will be equal and opposite. So this value have the same actually. Now we can see that at impedance at resonance is equal to R. So at resonance, this Z is equal to here. So Z is almost constant. So at this frequency, it is R is constant. This is our Z. The Z is the impedance. So impedance is something shaped like this because it is called parabola. Because Z, you can say that Z is equal to what it is called impedance. It is under root of R square plus XL minus XC square. So this is shaped like this, a parabola. So effectively, this X will be equal to like that. At this point, it is equal to 0. The reactance is equal to 0 at this point. Before this or the value of frequency less than FR. When the frequency is less than FR, that is a resonance frequency, it is called the capacitive or leading current is there. And if the frequency is greater than the resonant frequency, it is the inductive or the lagging current. So this is for the capacitive and this is for the inductive circuit is there. So this is the you can see the characteristics of the some reactances, impedances. Now let us come to this this side here. In this side, this is the power factor and the current. So we know that this is the impedance and the current. We can say that it is the inversely of this of impedance. So current in the flowing in the circuit is equal to or proportional to the impedance. V by Z is this. If V is constant almost, so current is almost inversely to Z. So its shape is almost inversely of that. You can see that. So at some, suppose it is the minimum value of current is impedance. So here at this point I have the maximum current. Okay. Similarly, power factor here. The power factor shape will be like this same, and the power factor is maximum at resonance frequency at this it is 1, and the current is maximum at this point. We call it the maximum value of current. So from this diagram or this expression, it is at resonance frequency it is resistive. Before the resistance frequency, if the circuit is working at the frequency less than the resonance frequency, it is behave like a capacitive. And if the resonance frequency is greater than the resonance frequency, it is basically inductive or lagging current is there. So this is how our current is changes here. Okay, initially current is increases and then it is become maximum and then it is again decreases. So this is the variation of the different parameters with frequencies there. Next is the quality factor or the Q factor of the series resonance. Now, if we talk about this Q factor is very, very important because it basically tells us the quality means that or simple with the voltage magnification of factor. We call it a voltage magnification factor. So it is nothing but it is the ratio of this is nothing but the VL upon V or VC upon V. So this VL, we know that nothing, VL is the voltage across the inductance, which is nothing but the current into XL because the drop, and again how much I into R, because at resonance it is equal to R. So you can simply write it like a XL upon R, which is written over here. And what is XL? It's omega R L upon capital R. So this is the Q factor. You can easily calculate the Q factor from both things. Either it is this or VC upon V, that is equal to 1 upon omega R CR. Clear this thing? So this is called the voltage magnification factor, and it is nothing but it is the ratio of the two. So here the coil resistance is often on resistance. The Q factor is sometimes referred to the Q factor of the coil. The Q factor something we call the factor which is the Q factor of the coil. because it's associated with the coil also. So Q factor, how we can determine the value of Q factor? It is, you can simply say that with the help of this we know that this is the resonance frequency. So with the help of this we know that this, and Q factor can be, if we put over there these values over here, you will get the Q factor. So it is equal to, Q factor is equal to XL upon R, which is equal to omega L upon R, and from here we put the value of this R, that is 1 upon root LC. So this Q factor will comes when we put the value in equation number 1, we will get this result. That is 1 upon R, L by C. R is the resistance, L is the inductance, and C is the capacitance. So this is the Q factor of the series resonance. So we can express this in terms of inductance and capacitance. Now after that, there is one of the important terms we call the bandwidth of series RLC circuit. So bandwidth of the series RLC circuit is the range of the frequency for which the circuit current is equal to or greater than 70.7% of the circuit current at resonance. So it is nothing but the range of the frequency for, you can say that, frequency for which the current is equal to or greater than this value, that is 70.7%. So let us through this graph, suppose that this is the maximum value of current. Okay, this is the IM, which is called the Imax, matlab maximum value of current, and the 70.7, it is almost 1 upon root 2. So 1 upon root 2 is equal to hota hai, it is 1 upon root 2 means 0.707 times of maximum value of current. So at this value of current, we can find the power actually. So power is equal to I square into R. So power is nothing but it is equal to Imax upon root 2 square into R, because at resonance the power will be maximum because the current is maximum and the value of current is Im upon root 2, means at this point. So at this point the current value of current is this, that is I m by root 2. This is the value of current at maximum power. So maximum current is this is the half power. So at this half power, because the power is half, so you can say that Im square upon 2, Im square R into upon 2, that is half of this power. So at this power, your current is this, value is this, the value of current is this. So here you can say that the F1 and F2 are the limiting frequency at which the current is exactly equal to this. So at this, from this figure, so these are the two frequencies, F1 and F2 are called the limiting value of frequency of this range. So the frequency F1 is called the lower cutoff frequency, and the frequency F2, which is on the higher side, is called the upper cutoff frequency. So lower cutoff frequency, and this is called the upper cutoff frequency, and this is the bandwidth, is the range between the upper and the lower frequency. So you can write that the bandwidth is equal to the difference between the upper and the lower frequency, that is F2 minus F1. So simply you can define the bandwidth that the difference between the half power frequencies F1 and F2 at which the power is half of its maximum, because at this point the power is almost equal to half and the value of current is 0.707, that is called the 70.7% of this. So between these two frequencies, this circuit value or the current value of current is more, then it's 70.1. So that's why this type of circuit is also called the acceptor circuit. Okay. Another point in this is called, or after this half frequency, we can also find the value of half power frequencies if you can calculate the bandwidth. So, and you have the FR. So F1 can be equal to your, this will be equal to your bandwidth. This is your bandwidth. This is suppose your delta F. So F1 is equal to your f2 must be equal to the bandwidth plus your delta f, and f2 is equal to bandwidth plus delta f. So this you can calculate subsequently. Okay. Next is our some example based on this. So in this numericals, you can see the coil of resistance 100 ohms and inductance 100 ohms resistance and inductance of 100 micro Henry is connected in series with the 100 picofarad capacitor, and the circuit is connected to 10 volt variable voltage source. Calculate the resonance frequency, calculate the current at the resistance, voltage across L and C, and Q factor. So these are the some data that we have to calculate. So resonance frequency we can calculate by using formula 1 upon Fr is equal to 1 upon root pi and 1 upon root pi and root LC. By direct summation of the values, you can find this value of the frequency in hertz. Then current, if we have the value of current, means voltage upon resistance, because at the resonance the current is maximum and it is equal to V by R, because the resistance is the impedance is minimum, equal to value of R. So R is 100 and the value of voltage is 10 volt, so you can calculate it as 0.1 ampere. Another third, the voltage across L and C. For finding the value of voltage across L and C, we have to calculate the XL and XC. So XL is equal to omega 2 pi Fr into L. So this is your 1000 ohm XL, and based on this, where VL is equal to IR into XL, that is equal to 100 volt. Similarly, you can calculate the resonance. VC is equal to IR into XC. XC is equal to 1 upon omega C. So when you multiply with the current, that is equal to 0.1, it will be 100 volt. So you can see that at resonance, VL and VC is equal, but they are in opposite direction. Okay, they are in opposite direction. And subsequently, we can calculate the Q factor, which is 1 upon R under root L by C. So we can put the value of all the parameter and we'll calculate the value of 10. So 10 means it is a Q factor, quality factor is of the circuit. Okay, it is called the voltage magnification of the circuit. So the voltage across the inductance will be equal to 10 times the voltage of the source voltage. So you can see that the 100 volt is the voltage across the capacitor, and here is the 10 volt is the variable supply. So this is the at resonance. So this is a small example of the series. Now let us come to the parallel resonance. In parallel resonance, so these are the points at which we are going, like the key points. What are the key points? Resonant frequency in case of parallel resonance, then impedance of the parallel resonance, we call the dynamic impedance. Q factor is there. How can we found the quality factor, and then comparison with some numericals also. Okay, so let us start with the key points. In the key points, that the circuit power factor is unity in both the resonance, both the resonance series and parallel. The important part is that the circuit power factor is unity, so that this it will behave like a pure resistive circuit. When there is a unity power factor, that means the circuit is behaved like a pure resistive circuit. Since the parallel resonance circuit is resistive, it means that in parallel the circuit admittance, the admittance is given by conductance plus susceptance. It is a real part, it is an imaginary part. So circuit admittance is equal to circuit conductance only, because the imaginary part will be equal to 0 here, because it is real. Okay, so that is, it is equal to circuit conductance. Here the susceptance is 0, that is B is 0. So only Y must be equal to G, because this is our 0. Okay. Another point is the circuit impedance of the parallel resonance circuit is maximum. So in this case, what happens? The impedance is maximum, and because of that, the current will be minimum. So at resonance, the current is given by this. Okay, and the circuit impedance of the parallel is maximum. We will calculate it as a dynamic impedance. We will calculate it. So ZR is the circuit impedance parallel resonance. So this is the circuit impedance in the parallel. So let us find these values actually. Okay, so these are some key points as far as the parallel resonance is concerned. Okay, so let us find first the resonance frequency. For finding the resonance frequency, let us have a circuit where we have a coil or resistance and inductance is there, capacitor is connected in parallel, and this is supply. So this is the current flowing in the inductive circuit IL, current flowing in the capacitor IC is there. So and I is the total current actually. So this is the called circuit. ZL is called the impedance of the coil or RL simple, the combination of RL. So here you can say that IL is the current flowing through this because they are connected in parallel, the voltage will be same for both. So IL is equal to V upon ZL, where ZL is this, and IC is equal to V upon XC, where XC is equal to 1 upon 2 pi FC. That is called 1 upon omega C. So these are the two value of current IL and IC, and current I is the phasor sum of both. Phasor sum of both. Now what happens if we draw the phasor diagram of this? If we draw the phasor diagram of both, so voltage, if we take the voltage as a reference and the current IL, which is flowing in this inductive circuit, and in inductive circuit we know that the current always lag the voltage by some angle depending on the value of R and L. So suppose that this is the value of phi L. So current, this is the V, and this is the IL, which is lagging behind the voltage by some angle called phi L. Okay. Now IC is the capacitor current, which is the capacitor in capacitor current in the leading. So the current lead the voltage by 90 degree in pure capacitor. So current lead the IC is lead the voltage by 90 degree. And if we calculate the phasor sum of both, the voltage and the current are in the same phase at resonance. So at resonance, this voltage and this current are in the same phase. Okay, and this part will be equal to your, this must be equal to this by symmetry. So here you can say that after understanding about this circuit, what is the value of current in inductance, what is the value of current in capacitor branch. Now let us find the resonance frequency in case of parallel resonance. So for at resonance, we know that IC is equal to IL sin phi. IC is equal to IL sin phi. This came from here. So IC means this IC is equal to IL sin phi. These both are equal at resonance. This is nothing but the reactive component. This is the active component of the current. This is the reactive component of the current. IL sin phi. Okay. Now this is equal to this. Now substitute the value of IC and IL. V upon XC is equal to V upon ZL, and sin phi L is equal to XL upon. Simply we can draw the triangle impedance triangle. So this is your if it is phi, this is R, this is ZL, this is XL. Okay. So simple sin phi L is, you can write it as phi L. So sin phi L is equal to XL upon ZL. Yeah, it came from here, called the impedance triangle. So XL upon ZL. So this comes V into XL upon this, and ultimately it is equal to ZL is equal to XL to XC, which is equal to your these terms. So if we expand this ZL R square, because Z is equal to the ZL is equal to your R plus JXL. This is the impedance of the inductive coil actually. So if we expand it, so R square plus 2 pi F R L square is equal to XL, that is equal to omega into L. So omega is 2 pi FL into 1 upon omega C this. Simply we are substituting value this, and if we solve it, we will get this expression. Ultimately, this is the value of FR. It's called the resonant frequency of FR. The resonant frequency. So this is the expression for the resonance frequency in parallel circuit. Okay. Now, after this resonance frequency, which is based on the value of inductance and capacitance and resistance, now find the dynamic impedance at resonance. The dynamic impedance at resonance, the value of impedance, we know that it's a maximum value. Okay. And what is the value of the dynamic impedance? Let us say it is ZD, and this is the maximum at resonance. So at the current drawn by resonance is minimum. So if the impedance is maximum, that means the current is almost minimum. and the parallel circuit at resonance is called as rejector circuit. So it means that it is also called the rejector because the current is minimum, and current is minimum because the impedance is maximum. So let us find the value of this dynamic impedance. For this, we have this component called I is equal to IL cos phi. With the help of this, we know this thing is already defined. Now I is equal to IL cos phi is the active component. This I is the current and IL cos phi is the active component. IL cos phi L. So IL was this. So this is the projection of this IL cos phi. So I is equal to IL cos phi. So when we put the value of this I and I cos phi, IL cos phi, where this of course the current is this, and the current is equal to V upon IL is equal to V upon ZL, and this is R upon XL. We know that with the help of this R upon ZL is the cos phi, R upon base upon hypotenuse. So this must be equal to VR upon ZL square, and I is equal to VR upon ZL square. From here we can write L upon C. So it can be written in this form, that is I upon ZD, where ZD is the impedance called the dynamic impedance. So L by CR. So ZC will be equal to your L by CR. So you can easily calculate or find the value of dynamic impedance if we have given the value of inductance, capacitance and resistance. So this is the dynamic impedance. This is how we can calculate it. The next, after this dynamic impedance, we have the quality factor of the parallel circuit. In the quality factor, again, I told you that it can define as it is the current magnification. In case of series resonance, it was the voltage magnification, but here it is called the current magnification. So it is given by the current in the inductive branch upon the current in the supply, whatever subcurrent we are supplying. So this can be written in this form, and if we put the value of current by IR, this is V by ZL, and the current supply at resonance, this is we have already calculated V by ZL, and if we put the value of this part, we find that it is equal to 1 by R L by C. So 1 upon R L by C. The formula is same for both, but its meaning is different quite, because here the quality factor is defined in terms of current magnifications. Earlier in case of voltage magnification, it was defined as the voltage magnifications. So these are some numericals we can solve with. Now the important part is that how we can compare it. So when we compare the two, in case of impedance at resonance, then series it is minimum, while in case of parallel it is maximum. Current, of course, in series circuit the current is always maximum, and in parallel it is minimum. Power factor at resonance, it is unity in both in series and parallel. Resonance frequency is given by this, and in case of parallel it is given by this. The formula is different actually. When the frequency is less than FR, that is resonance frequency, circuit is capacitive. Here the circuit is inductive. When the frequency is greater than the frequency of resonance frequency, the circuit is inductive, while in case of parallel it is capacitive. Q factor is given by this, Q factor is given by this. It magnifies voltage, it magnifies current. So these are some difference or the comparison between the series and parallel resonance actually. So this is basically all about some basics or some introduction of the resonance, series resonance and parallel resonance. Okay, thank you so much.